So as many of you know, you have seen this. This is like the top 500 chart. We crossed as a community 100 petaflops in 2017. So 2018 onward is the summit, which is the #1 system. And of course, in the community, we are waiting for the exaflop systems to come. And depending on the different countries are working on, we may see like a machine coming up with in 2020 or 2021. So in this context, there is a lot of discussion taking place, like how do we design these systems, not just for the traditional HPC or scientific computing, but also trying to take advantage of the big data and deep learning together. So that is the kind of the challenge we want to achieve. And not only we want to achieve these kind of things on a dedicated environment, but also we want to achieve this in the cloud. So what do I mean by this kind of convergence? So this is like kind of my definition, or in our group we are pursuing, but this is very similar to what a lot of other people are also focusing on. So assume that you have an HPC cluster, just like a bunch of nodes, CPU, GPU together. You have some resource manager like a Turk or Slurm or Sun Grid Engine. You name any one of those scheduler, and then you have also different kinds of parallel file system. Lustre, GPFS, BGPFs, any of those file systems. Now the question is, traditionally, these have been used, these kind of environments, to run purely scientific jobs. Like a MPI kind of thing, you have the MPIs available as modules, and the end users come and link their applications to the modules and proceed. But what we want to achieve is not just like the MPI jobs are running, but exactly on the same system, we can also run a Hadoop job, we can also run Spark job, we can also run deep learning jobs, and all of those can be coexisting at the same time. So that is the kind of a challenge what we are trying to achieve. So if we can achieve this, then obviously we don't need all different kinds of clusters, like saying this is an HPC cluster, this is a big data cluster, this is a deep learning cluster, and then we need to exchange huge amount of data between these clusters. Then those are not efficient, so we want to run everything on the same system. So that is the context in which I'll be trying to go over some of the things what we have been doing in our group, and we already have solutions trying to provide this kind of a convergence. So I'll take it into 3 parts. First, focus on the Novice Project, which I introduced a little bit yesterday, MPI one. Then I'll go into this high performance big data analytics library, that is the HIVD project. We call it high performance big data. And then of course, high performance deep learning. So if you take a traditional like a parallel programming perspective, of course, MPI has been the dominant parallel programming model for scale out. Shared memory you still use within the node, and especially in the modern systems, as the number of cores per node are increasing, in fact, shared memory is also playing a big role. Either you can use like a MPI plus OpenMP kind of environment, or you can also purely use MPI within a node also. So the sockets to sockets or the cores to core can directly talk in an MPI. So in fact, as the number of cores per node are increasing, in fact, it is becoming very important to optimize communication within the node. Okay, if you don't optimize that, you may not see actually good performance as you scale up. So this is the Novice project I introduced. Many of you were here, so I don't want to go into details. This is the project we started almost day 1 of InfiniBand. We had the very first demonstration of the MPI running over InfiniBand in 2002. And then after that, we have been continuously working on and enhancing it. This project is in its 18th year and is very widely used. We crossed like a 500,000 download last November just from our site, currently being used by more than 3,000 organizations. And also these are being used in a production environment in very large scale systems. So currently, in fact, I am working very closely with the TAC, Texas Advanced Computing Center, that is the Frontera system, which will be a formal dedication will happen coming Monday. That is kind of a 35 petaflop system in the US academia. This is the largest system, will be available to all the academic researchers. So this is the kind of the quick overview of the release time download. We are in a very upward trajectory here. So this also I introduced briefly yesterday, but the broad idea is that in the same stack, we are able to bring all these different, at least the HPC and DL together, Big data is separate. I'll talk about that, but the architecture falls into a similar kind of environment. So here, even though the project we started with InfiniBand, but it supports also IVAR, Rocky, Omnipath, and very recently we also supported the Amazon AWS, the new high performance adapter. It's Elastic Fabric Adapter, or they call EFA. And we support again all the different kind of the multi-core, many-core platforms. We support all the programming models, but this is the secret ingredient where we actually try to come up with this very high performance, scalable communication runtime, highly optimized for all these different networking technologies and platforms. So then we have different versions of the library I introduced, but today I'll only be touching the first three, the basic MHP2 version, then there is an advanced version, we call it MHP2X, like heading into the Exascale, and then I'll be talking about this GPU direct RDMA. I also introduced that yesterday a little bit for highly optimized for GPU cluster. So from the HPC side, we try to provide these solutions in multiple domains, people trying to take advantage of the best performance and scalability for CPU-based systems, the GPU-based systems, hybrid. So these are the three software packages are available for that. So this is the kind of provides a very quick overview of our MHP2 library's performance over the years with all different networking adapter. Okay, I didn't go back to like a InfiniBand, SDR, and DDR. They have become ancient, but starting from like this QDR, FDR, EDR, Omnipath, and then the latest one is ConnectX-6 SDR. So the left-hand side is trying to show one-way latency, that is half of round trip. So we can see like we are hovering around like a 1 microsecond here. And then for larger message latency, it depends on the bandwidth. If the network has higher bandwidth, you will see better latency. So that's why this the ConnectX-6, which is the HDR, 200 gigabits per second, is trying to give you the best performance. So these are the bandwidth, unidirectional and bidirectional. So here you can see over the years how things have evolved. This is like a QDR, FDR, dual FDR, EDR, and this is the EDR. So you can see this is around like a 24.5 gigabytes per second. If you do a multiplication by 8, it's coming very close to 200 gigabits per second. And the right-hand side is the bidirectional bandwidth when both the nodes are talking to each other. So ideally, we should be getting 50 gigabytes per second. So here it is a little bit lower. We are getting around 48 gigabytes per second. So these are the point-to-point operations. But when we design these MPI stacks, we try to do a very holistic design. In the sense, if some of you are familiar with MPI, there are so many calls. You have two-sided, one-sided, collectives, all kinds of dynamic process management. Just MPI standard allows people to write and use all these different primitives. So for all those primitives, we do very highly optimized design. And one thing there, a lot of people ignore, and we have been continuously focusing on this, job startup. In fact, today morning, the Azure person also highlighted on that. So whenever these systems are becoming larger and larger, the biggest challenge people are facing when the people come and start deploying the system, how much time does it take for an MPI job to run on the entire system? Okay. In fact, this is a big challenge. If just the job startup takes, let's say, for 10 minutes, you are wasting a lot of resources. Okay, and especially in a commercial cloud environment, you are still being charged for all those time. You're not doing any actual computation, but you are paying for just the job startup. Same thing happens if somebody wants to do debugging and all. So we continuously over the years have been focusing not just to purely provide the basic communication performance, but also startup. So these are the numbers from very fresh, from the TAC Frontera system we are working on. So here you can see like a 57,000 processes, MPI init. We can finish in like a 3.9 seconds. Just count like 1001, 1002, 1003, 1004. Your 50,000 processes have already been launched. Your MPI init has taken place. Okay, so jobs have started running. And here the comparison, we show like an Intel MPI. We perform far better than Intel MPI. And obviously over the years, we always like start pushing these new designs, and all other MPI stacks again follow and take similar kinds of designs. That is okay with us, but this has been one of our greatest new kinds of designs we have been pushing. So then, of course, the point-to-point collectives play a very big role. I indicated that yesterday. Not only it's for short messages, but now with all the deep learning workload, medium and large messages are also coming into play. So continuously we have been innovating, and this is a new design we had presented at the Supercomputing 2017. So here if you see, like, this was taken on the TAC Stampede 2. It has a KNL plus omnipath system with 10,000 processes. With a new kinds of designs, we are able to improve the performance by factor of 2.4. Okay, just like in this case, it is an MPI all reduced. So if you improve the performance for all reduced, then you will see all your jobs, even the deep learning applications, will run faster on these things. Then I also introduced this new kernel-based designs. This is the XPMM. So that is the kernel module which is currently being available. That is the very latest one. The field has gone over a lot of enhancements. In fact, 18 years back, from our group, we were the very first one to introduce this kernel module. If you do some search on the literature, we had introduced something called Limbic. That was the first kernel-based module we introduced to have very fast communication from process to process within the node. And that was our own kernel module. A lot of people used it. But all those ideas have gradually gone into the standard Linux kernel, and that is called CMA, cross memory attach. So those calls are available, and we also support that. So that's like the second generation came, and the third generation is coming, which is the XPMM. So it basically allows to map my process, the entire virtual address space, to the other process virtual address space, and vice versa. So then when the processes within the node are talking to each other, instead of sending messages, they can read and write. That is much more faster than sending messages. So in that case, based on that, point to point, we also support collectives. And these are already available in this MapIs2X thing. It is also available on the Azure and all these new kinds of environment. And you see very significantly here, all reduced, we can give you a factor of like 1.8x, 4x improvement kind of things in latency. So then another thing people have been struggling over the years in the MPI design is how to overlap computation with communication. Okay? Those of you who are familiar, at least from the application perspective, ideal thing is that you hide all the communication. If you get 100% overlap, you get the best performance, scalability, but that is very hard. So one thing what limits is that if some of you know the MPI internal protocols, there are broadly two protocols. One is an eager protocol, which is for short messages, and there is a rendezvous protocol, which is for large messages. Okay? So when you try to send a large message, typically what you do is you try to do some handshake. Like I tried to send you a RTS saying that, are you ready to receive? And then if you are ready, you send me a CTS with a buffer address, and then I can do all these RDMA-based operations. But the big challenge is that if you have already entered a computation, even though my request has reached you, you are not able to send the CTS back. And this is where in most of the applications you lose performance, because you are not able to achieve overlap. So people have worked on, over the years, asynchronous progress design. So that means periodically in the code, you try to put saying make progress, make progress. So that means you touch the communication library and then see if somebody has sent you a RTS, and then you try to send the CTS so that the communication can make progress. So that is the whole idea of asynchronous progress. But the question is how you do that. And most of the designs in the literature have used some separate threads or separate cores. If you go through that, then you are wasting resources. So that means I can take a 48 days. In fact, some of the benchmarks, people try to show you the best numbers. If you go internally, that's what happens. Like you might have a 56 core node. Actually, people are running on 28 cores. The other 28 cores are like working like assistants to make progress, and you get very good scalability. But that is, we are wasting half of the resources. So here we came up with a very new design. It was presented at Euro MPI 2018, and now it is available in our public release also. We don't need any additional threads or additional core. Okay? So internally, exactly using the full subscription, we can give you asynchronous overlap capabilities. And if you look at the numbers, so the left-hand side is like a P3D FFD, lower is better. The right-hand side is HPL, higher is better. You can see comparing with the latest Intel MPI 2019, you can get significant reduction in execution time, and also even the HPL performance. You can boost performance. And these are very simple runtime variables. You just have to turn on these variables, and then you get this kind of benefits in the performance. So I'll strongly encourage people to try out these kind of things. So then with respect to like different processor, it's as I said, like we have been focusing on all the different things, not just like x86, open power. Here we are trying to show some numbers, intra-node numbers, comparing Spectrum MPI, which is the production vendor MPI for the open power environment and our stack. Here if you see like this is an intra-node, so within the open power core to core, within the same socket, we are able to do MPI level communication in 220 nanoseconds. So that is the kind of the design we have put together so that to get the best performance benefit. So then I talked yesterday, how many of you were here yesterday's talk? I think most of you were, okay. So this is like the CUDA aware MPI I introduced. This concept was introduced in like 2011. So the idea is that if you have a GPU cluster, instead of doing a CUDA mem copy to host and then sending MPI send, MPI receive, where you don't get good performance, we can, if somebody knows how to write an MPI program from the host, instead of host buffer, we just said send device buffer, and the receive, we said receive device buffer. That's all you need to say. And then the MPI library takes care of all the transfers, and here also the GPU direct RDMA technology helps us because if the GPU adapter and the InfiniBand are on the same PCIe bus, instead of going to the host, we can actually do the first data transfer. So that is the whole concept we introduced in 2011, and of course a lot of other people have taken almost all other MPI libraries support this feature, delivers high performance and high productivity. And this is the number I indicated also in yesterday. If you do this kind of designs, taking advantage of GPU direct RDMA, there is also a library from NVIDIA called GDR Copy. If you put everything together, you get like a very fantastic performance. From GPU to GPU, I can do the data transfer in 1.85 microseconds. That is for very small messages. Medium messages, you gain quite a lot. Now, if you see the application level benefits, this is like a HIVD Blue, which is a molecular dynamics application. So you can clearly see the difference. This is the basic MPI 2 version. This is the MPI 2 with the GDR version. Higher is better. So you can see like as the system size increases, you are able to, in fact, give double the benefit in twice the performance by just selecting the appropriate library and triggering the appropriate operations. And this also I indicated yesterday. I didn't show all the results. So we have been working very closely with Switzerland Supercomputing Center for the last 3.5 years. This library is being used in the real-time weather forecasting. So we have been working with CACS as well as Meteo Suisse. That is the weather forecasting agency in Switzerland. So in a three-way collaboration with funding, we are able to really drive a national weather system in Switzerland. And continuously we have been innovating. There are a lot of, this application uses a lot of data types, and we are continuously optimizing on those data type performance from GPU to GPU to, in fact, give higher performance continuously. So this is trying to show a very high-level perspective of if you take like across a lot of different applications, there's like a spec MPI 2017. If you compare with the Intel MPI 18, here you can see like our version is able to deliver you much higher performance compared to the Intel MPI version. These are some numbers from Stampede 2. These are like large-scale scientific applications. Here you can see very easily, just out of the box, people are able to scale their applications to 4,000 core, 8,000 core kind of things, which run on these systems on a day-to-day basis manner. So then very recently, just a few weeks back, we introduced this new release for Azure. So if you go to MPI's webpage, in fact, we have a click. So what we have done is, it is a one-click deployment. Today morning, Dr. Gujrati indicated all those cloud setups and all those things. In fact, if you try to use our stack, you don't have to go through all these things. You can go to MPI's page, if you have online, just click this, and it will directly take you to your account, and everything is populated, then start using it for your applications. So it makes very easy for people in the Azure environment to use our stack with very good performance. So here if you see some performance, these are like Radix. So this has been taken on the HC. So these are the HP HC series, new series with native InfiniBand support Microsoft Azure has used. So here you can see like, sorry for the little bit overlap here. So compared to like HPC-AI, we can give you almost 3x factor. So you can see, like, as the system size are increasing, we are able to, in fact, really deliver performance compared to the HPC stack. So same thing happens on the also right-hand side on HB. So we also worked recently with AWS. As I told, AWS traditionally have been using only Ethernet. So now they have a new adapter called EFA. How many of you have heard of that? Okay, some of you. It is a newer adapter using a lot of new kind of protocols. And one such protocol they have introduced there called Scalable Reliable Datagram Protocol. So it is not InfiniBand, but it still uses a lot of these RDMA kind of concepts in their adapter. So we did a new design of our MFS2 stack for Azure. And similar kind of things you can see here. We presented this paper, in fact, 2 weeks back at the Hot Interconnect conference. And here we are trying to compare like some results like Mini-Ghost and Cloverleaf. So we already have a design based on unreliable datagram, but that again, unreliable datagram gives a lot of overhead to add the reliability. So this is our new design, the green one, with MFS2 XSRD. And then we are comparing here with OpenMPI, which has been running in their default mode. So once again, you can just, if you want to get really good performance on these cloud environments, the end goal, people have been using cloud to actually run your things faster if you cannot do it locally. And then if your job is running longer time, you are paying more. And so we are allowing people to run the same exact job with a faster so that your savings will be bigger, okay? So that is the kind of the goal we are trying to keep and working with all these cloud providers to deliver very high performance. So then let me move to the big data stuff. So these are the purely HPC. Then we also have been looking at a lot of these stacks which are traditionally being used in the big data analytics. So here if you see, like, this is a typical picture of the data center. So in the front end tiers, we use like components like Memcached, HBase. Back end we do MapReduce, Spark, those kind of components. So what we have done is, so we have taken a lot of these. So this is like, this project is going on for last 8 years. Hadoop, Spark, HBase, Memcached, Kafka. If you download those standard Apache versions, you will see that they only have, in the communication, they use sockets. And then sockets typically use the traditional Ethernet, but InfiniBand also you can run with the IP over IP mode, okay? But then you don't get the best performance. So what we have done is, based on our experience, what we learned from the MPI, we have taken a lot of those knowledge to this side. So we have a RDMA version of Hadoop, Spark, HBase. So these are all publicly available. This project is called High Performance Big Data, or HIVD. You can just go and download here. So these versions are being available for x86, OpenPower. We also have support for Singularity and Docker. Currently, there are around 300 organizations with more than 30,000 downloads that they use these stacks. So here again, like over the years, we have been getting a steady download for these stacks. So internally, if you see, this is where that convergence we have tried to put. If you take a look at the Apache Hadoop architecture, it has a lot of components. It has an HDFS component, MapReduce component, RPC component. So inside these, we have brought a lot of innovations to use all these RDMA components, and not only just to accelerate with RDMA. Here, if you see, we have an integrated Lustre. So that means if your HPC environment is using Lustre, you should be able to directly take the data from the Lustre. You don't need even HDFS. Then similarly, what we have done, like a very integrated scheduling with Slurm and PBS. So that is the kind of the things what is available in the HPC environment. So you directly, we have interfaces so that your job can be just linked to your Slurm scheduler or PBS scheduler. And if you look at the performance, I showed some yesterday. This is like the Hadoop 3. So you can see that it's exactly the same hardware. This is the test DFS IO latency. Lower is better here, higher is better here. So you can see we are able to significantly provide benefits. Just the software stack, you change exactly on the same InfiniBand or Rocky system. Using our RDMA library, you will be able to get good benefits. So this is, again, we are continuously working on this. There is a new feature which is coming up called eraser coding. How many of you have heard of that? Okay, so that is the new thing which is coming. In fact, Mellanox adapter also allows to offload some of these capabilities. So we had a paper at HPDC presented, so we are taking those designs and trying to integrate. So our next release will have, in fact, the eraser coding support. So the broad idea here is like this. As I indicated, so not only your MPI jobs are running, just like if you're a sysadmin, you take different kind of MPI libraries and make them available as modules. The same thing you can do here for the big data stack. You take our versions, it has a lot of parameters based on your system configuration. You can configure it and make it a module available. So that the end user who wants to use like a Hadoop or Spark, they don't have to go through all those builds. And they can just select and then start using your stack. In fact, we have been collaborating with the San Diego Supercomputing Center. If some of you have accounts there, it has been set up like that on the Comet. So anybody can just come and then use those stacks for the Hadoop and Spark directly without doing any additional work. Similar kind of things we have done for the RDMA for Apache Spark. Here you can see like a high bench page rank time. Similar kind of benefits we can see. This is an InfiniBand cluster with 768 cores, 1536 cores. We are able to give you, through the software stack, we are able to give you benefits compared to the regular version. So here again, same thing you can do. If some of your users are Spark, so download it, configure it, and make it is available to your end users so they can also run Spark on your HPC cluster. So then the distributed deep learning, I spent a lot of time yesterday, so I'll just give some little bit of highlights. I don't want to repeat all those slides. Broadly, as a community, as I said, people are trying to go for both scale up and scale out. And there are a lot of different solutions are available. We are heavily focusing on the MPI side, gRPC side, also on the big data side. So we are trying to enable the community to get the best scale up and scale out. So this is where we are trying to provide 3 different stacks, MPI to X, MPI to GDR, and then RDMA TensorFlow for the different people to take advantage of it. So I talked a little bit about this in very detail yesterday, but I'll just try to highlight 3-4 slides. So we are trying to enable the community to get the best CPU-based deep learning, GPU-based deep learning, and also RDMA-based thing. So I talked about these XPMM-based designs earlier. So that helps significantly in terms of the collective I showed earlier. So if you use these kind of operations, use our MPI to X library and turn on with XPMM support. Here data is like trying to show like a CNTK AlexNet training. You can see compared to other libraries, you will be able to get benefits at the application level. I showed this result yesterday. I want to again stress that. So this is on the #1 system summit. So we are comparing with our MPI-based design with the Nickel 2. That's the latest 2.4 version from NVIDIA. And if you just take a look at all reduce, we are able to give you far better performance compared to Nickel 2. This is the latency. Even as the number of message sizes are increasing, we are trying to give very good performance in bandwidth. And as the system size is scaling, there also we are able to give very good performance compared to even Nickel 2 and also OpenMPI and Spectrum MPI. Okay? So all these things actually have been, we have made this release MPI to GDR. There is a single flag you just turn on saying enable with TensorFlow. That's all you need to do. Run it. It's integrated with Horobot and TensorFlow, so you should be able to get this kind of performance on any of the GPU cluster. And I also showed this number. This is the largest we have run. Imaginet 1K. It has 1.2 million images. So this is also run on Summit using 1536 GPUs. So in fact, with the NVIDIA Nickel 2, it started failing beyond 96 GPUs, but we were able to scale to 1536, and we are able to train it in 5 minutes, 5.5 minutes, 1.2 million images kind of thing. So that shows the powerfulness. If you design an underlying runtime properly, you should be able to take advantage of it at a higher level. So all these libraries also available in container. There is a lot of discussion these days with the Singularity Docker. So we are trying to provide our libraries also for the cloud environment. As you can see the performance, this is like the MPI to GDR with container, very little degradation in performance. So you get almost the same performance as your native environment. So you should be able to use it in your cloud or container environment. So then I also talked about this RDMA over TensorFlow. I showed this number yesterday. So we have broadly taken the TensorFlow. People go through the gRPC, which is the Google RPC. So that Google RPC, we have done very highly optimized design on the InfiniBand RDMA, so you get very good performance with that. So this is also, you can do the same thing if you have a lot of TensorFlow gRPC user in your environment. Just download our things, make it a module available to your users, so they should be able to run these jobs in conjunction with all the other jobs which are running on the same system. So with this, let me conclude here. As we've been seeing that the upcoming Exascale systems needs to take a very holistic perspective of how you design that, both for the HPC, big data, and deep learning, and also cloud. And that's what exactly what we have been doing in our group for the last almost 20 years. A lot of people have been talking about these concepts, but we have solutions. These solutions are already available. A lot of people still, I call them slideware. They talk ideas that they need to be converged and all, but we have solutions, and people have been using this, so you are very welcome to also use this. I talked about this also yesterday. So this is the new development for the last 2 years. Besides providing support from the university side, now we have a commercial offshoot. If you really need a commercial support, we can work with you as an end user or end HPC center, or in fact, we can also participate in the bidding. All the options are now open. So we can work with a lot of people to provide all these solutions. So in fact, we have been working with Lawrence Livermore, a national lab, for the last 2 years to provide the MPI support for their all environments. We not only optimize our library on those systems, we also provide extending help to the application developers. Because as many times you know, the MPI has so many parameters. If you directly work with the application people and adjust a lot of these parameters, you should be able to extract a lot of performance. And that's what we have been doing. We'll be happy to work with others. I also want to highlight this. We do an annual MPI user group meeting. In fact, last week, we did the 7th annual MPI user group meeting. So we bring a lot of these users together and try to discuss what works, what doesn't work, who is getting what kind of performance, what are the broad issues. So we had a very nice 35 organizations from 5 countries participated in this event. So if you go to this site, we simply called MUG. It is an MPI user group meeting called MUG. And so all these slides and videos are available here. In fact, some of them have started coming through Inside HPC also. So they have recorded all the talks, so please feel free to take a look at these. We had very experiences from all these people from all over the world about their experience. So with this, I'd like to thank again all our sponsors, and also all my past and current students, staff. Those are all my heroes. And I always try to give credits to them whenever I talk. They are doing the hard work there. I'm just coming, having fun here in Perth. And I also indicated I continuously look for newer students, staff. So if any one of you are interested, and so that you come and work and your name goes to that other slide in a few years, okay? So please contact me. So with this, let me stop here. And if there are any quick questions, I'll be happy to answer. Otherwise, I'm still here throughout the evening, and I'll be happy to talk with each one of you. Thank you.